Recently, in one of my weekly live streams that I typically do every Monday night at 5 o'clock Pacific time, I went over an example problem that involved finding the critical numbers of a log function. And finding the critical numbers in a log function can be a little bit tricky because there's a little bit of an extra step that you want to think about as you're doing this. Because of that, I thought you might find it helpful to get a video made about it. So I'm going to be showing you in this video a clip which actually came from that live stream where I talked about finding the critical numbers of a log function so that you can learn how to do this on your own. If that sounds good to you, be sure to stick around to the end of the video. And by the end of it, I bet you'll feel a lot better in knowing how to find critical numbers of a log function. If you do want to hear the kind of conclusion of this problem where we kind of build on the critical numbers and talk about actually finding the local maximum and minimum values of this function, be sure to hit that subscribe button and that bell icon too, because my next video that I'm going to be coming out with is going to finish up the problem and show you exactly how to use these critical numbers to find the local extrema of this function. But anyway, without further ado, let's go ahead and jump into the example and I'll show you what I'm talking about. Find the local maximum and minimum values of f of x equals ln of x to the fourth plus 27. Okay, I'm gonna go a little bit quicker through this problem since I just kind of went a little bit slower through that last one. But let's go ahead and go through the same steps here. So the steps, whenever you're trying to find local minimum and maximum values of a function, you're always going to start with the critical numbers. So to find critical numbers, first thing you need to do is find the derivative of your function. To find the derivative of this function, we're going to have to use chain rule, which is one of the topics on my free Calculus 1 study guide. If you want to check that out, there's a link down in the description below. I also talk about chain rule, local minimum and maximum values, critical values. All that is covered also in my complete Calculus 1 package. Link to that is down in the description below as well. But the derivative of this is going to require chain rule, which says that we're going to take the derivative of the outside function, leave the inside function alone. So in this case, the parentheses make it pretty clear what we want to consider our inside function and our outside function. So what's in the parentheses will be our inside function. Our outside function is the natural log part of it. So the derivative of the outside, leave the inside alone. The derivative of natural log of x is 1 over x. So if we're taking the derivative of the outside, leaving the inside alone, we're going to get 1 over our inside function. And then chain rule says we need to multiply that by the derivative of our inside function. The derivative of x to the fourth can be found using the power rule. Bring the power down in front, leave the x as x, and minus 1 from the power. The derivative of a constant is 0. So our derivative is going to be 4x to the third over x to the fourth plus 27. Okay, once you find your derivative, the next thing you need to do in order to find critical numbers is to figure out where does f prime of x equal 0 and where does f prime of x not exist. In this case, we have a rational function. Our derivative is a rational function, which just means that we have a polynomial over a polynomial, a fraction where you have the top and the bottom of the fraction just being polynomials. When you have a, f prime, your derivative is a rational function like this, it's pretty easy to split up and find critical numbers because all you have to do, the only places where a fraction like this is going to equal 0 is where the numerator equals 0. So if we just look at 4x to the third and set that equal to 0, that's going to be the only places where this whole fraction as a whole equals 0, because 0 divided by any number is 0. And the only places where f prime of x might not exist is wherever the denominator equals 0, because we don't have anything else besides a fraction that could cause us to accidentally break the rules of math. There's no square roots, there's no logs in this function, but there is a fraction. So we need to be careful of dividing by 0. You cannot divide by 0. So if the bottom of a fraction equals 0, that means you're dividing by 0, which is against the rules of math. So what we can do is just take the bottom of our fraction and set it equals 0. Now we have these two equations that when we solve them will give us all of our critical numbers of our original f of x. So to solve this for 0 or for x, we can divide both sides by 4 and then take the cube root of both sides. So x equals 0 is going to be one of them. And then for this one, we can, again, let's basically just start to move everything over and get our x all by itself. So we'll minus 27 from both sides. X to the fourth equals negative 27. Take the fourth root of both sides. And notice what happens here. We're taking the fourth root of negative 27. You cannot take an even root of a negative number. So this actually does not exist. This does not give us a real number. So this equation does not have any solutions. There's no places, no x values where x to the fourth plus 27 equals 0. So as a result, we don't get any critical numbers from trying to figure out where f prime of x does not exist. But we do have this critical number x equals 0. So x equals 0 is going to be our only critical number of this function. Well, I hope you found that video helpful. Like I said, I'm going to be finishing up this problem and going over how to use these critical numbers to find local extrema of this exact function. So if you do want to see that video, it's going to be coming out very soon. Just hit that subscribe button down below. And if you're not watching this video right after it comes out, I'll come back and put it right over there so you can go check that out next. Thanks and see you next time.